Hello everyone, I am Muskan from Basic Chemistry Honors first year. My roll number is 21. Today I am going to read out the chapter Cycloalkanes. Cyclic aliphatic hydrocarbons or alicyclic hydrocarbon are hydrocarbon which contain closed chain or ring of carbon atom and resemble open chain or aliphatic hydrocarbon in many respects. Like aliphatic hydrocarbon, alicyclic hydrocarbon may be saturated or unsaturated in nature. Saturated alicyclic hydrocarbons are generally known as cycloalkanes. They have general formula CnH2n and are isomeric with alkenes. Nomenclature of cycloalkanes. Common name: saturated alicyclic hydrocarbons contain a number of methylene groups joined together to form a ring. Therefore, they are known as polymethylenes in the common system. Accordingly, the individual members are named by prefixing the number of carbon atoms in the ring before the word methylene. IUPAC system. In the IUPAC system, saturated alicyclic hydrocarbons are termed cycloalkanes. The individual members are named by adding the prefix cyclo to the name of corresponding straight chain hydrocarbon having the same number of carbon atoms as the ring. For instance, quite often alicyclic hydrocarbons are also represented by drawing simple geometric figures such as triangle for cyclopropane, a square for cyclobutane, a pentagon for cyclopentane, and so on. The presence of carbon atom at each of the corner and hydrogen atom attached to carbon is taken for granted. Nomenclature of substituted cycloalkanes. IUPAC names for substituted cycloalkane are by following IUPAC rule, which the student has already studied. However, some important points are given below. For monosubstituted cycloalkanes, there is no need of numbering to indicate the position of group. The cycloalkane containing more than one substituted numbering of carbon atom of ring is done in such a way that the substituted get the lowest possible number. Their numbers are prefixed in alphabetical order along with their position. Moreover, the substituent which comes first in alphabetical order is given the lowest possible number provided it does not violate the lowest set of locants rule. If the ring contains equal or more number of carbon atoms than the alkyl group attached to it, the compound is named as a derivative of cycloalkane, and the alkyl group is taken as substituent as already shown. If the ring contains lesser number of carbon atoms than the alkyl group attached to it, or if more alicyclic ring is treated as the substituent. In addition to the above rules for cycloalkanes, some important points for naming cyclic compounds containing multiple bonds and other functional groups are given below. If the carbon chain attached to alicyclic ring contains a multiple bond or a functional group, the carbon chain is taken as the parent and the ring is treated as substituent irrespective of the size of the ring. If a compound containing an alicyclic ring directly attached to a benzene ring, it is named as derivative of benzene. If the ring contains a multiple bond and the side chain contains a functional group, the ring is treated as substituent and compound is named as derivative of the chain containing the functional group. If a functional group containing carbon is directly attached to alicyclic ring, the carbon atom of this group is suitably included if the suffix used for the group. For example, aldehyde group is represented by the suffix carbonaldehyde, carboxylic acid by carbonitrile. Synthesis of cycloalkanes and their derivative. Only method number 3, 5 and 7 are included. The important method of synthesis of cycloalkane and their derivative are described below. Most of these methods, it may be noted, involve the conversion of some open-chain compound into a cyclic compound through the process is of cyclization or ring closure. The cyclic compound thus obtained may be cycloalkane or its derivative. If required, the cycloalkane derivative is further subjected to suitable reactions to change it into the desired cycloalkane itself. Addition of carbenes to alkenes. This method involves the addition of carbenes to alkene to form cyclopropane derivative. The reaction is also referred to as cycloaddition. Since free carbenes are too reactive to be isolated, the reaction is actually carried out by using a carbene precursor that generates the carbene under suitable experimental conditions. For example, when treated with diazonium methane or ketene in the presence of light alkene add-on carbene to form cyclopropane derivatives. Simmons-Smith reaction. In this method, action of carbene is carried out by treating the alkene with methylene iodide, zinc-copper couple to get cyclopropane derivative. Zinc-copper couple required for the reaction is usually obtained by heating zinc dust with copper chloride in ether in the presence of nitrogen. It is believed that methylene iodide and zinc react to form a carbene-like species called carbenoid. The carbenoid brings about the stereospecific addition of CH2 group directly to the alkene. Simmons-Smith reaction gives better yield of cycloalkane than is obtained by the addition of free carbene to alkene. Photochemical 2 plus 2 cycloaddition reaction. The term cycloaddition denotes an addition reaction between two unstable molecules to form a cyclic product. During this reaction, new sigma bonds are formed at cost of pi bonds of the reacting molecules. Individual reactions are designated by writing the number of pi electrons of each reactant in a square bracket. For example, a reaction between two alkene molecules to form a cyclobutane ring by using 2 pi electrons for each molecule is referred to as 2 plus 2 cycloaddition. 2 plus 2 cycloaddition reaction can be carried out easily in the presence of light but not under thermal conditions. Such reactions are termed as photochemical 2 plus 2 cycloaddition reaction. They may take place by a concerted mechanism involving cyclic transition state. Formation of substituted cyclobutane by photochemical 2 plus 2 cycloaddition of two alkene molecules may be represented in general as follows. 4 plus 2 cycloaddition dials adder reaction. Cycloaddition reaction involve addition of an alkene 2 pi electron referred to as dimethyl and conjugate dienes that is 4 pi electron to form 6-membered system. In contrast to 2 plus 2 cycloaddition, these reactions take place readily under thermal conditions. If the dienophile containing electron attracting groups such as C double bond O, COOH, C triple bond N, chlorine, the reaction takes place extremely easily, sometimes even at room temperature. It is interesting to note that 2 plus 2 cycloaddition reaction take place readily photochemically but not thermally. On the other hand, 4 plus 2 cycloaddition reaction occur readily thermally but not photochemically. Dehalogenation of suitable dihalogen derivative of alkane. Freehunt method. On treatment of suitable alpha gamma dihalogen derivative of alkane, that is dihalogen derivative having halogen atom attached to terminal carbon atom with sodium or zinc, they get dehalogenated from cycloalkane. The method may be regarded as an internal Woods reaction. However, this method gives good yield only in the preparation of cyclopropane. If the alpha and omega dihalide contain more than 6 carbon atoms, intermolecular Woods reaction takes place, giving rise to open chain alkane. Dachmann cyclization: when ester of certain dicarboxylic acids such as adipic acid and pimalic acid are treated with sodium or sodium ethoxide, they undergo intermolecular collision condensation to yield cyclic beta-ketoesters. The beta-ketoesters of hydrolysis and heating get decarboxylated to form cyclic ketones. The ketones are in turn subjected to Clemmensen reduction to get cyclic alkanes. Dickman method is most suited to the preparation of 5 and 6 membered ring. Pyrolysis of calcium or barium salt of dicarboxylic acid, Wilson's method. When the calcium or barium salts of certain dicarboxylic acid are heated strongly, they yield in a cyclic ketone. The ketone thus formed is converted into cycloalkane through Clemmensen reduction as illustrated below. In keeping with Planck's rule, this method is used for the preparation of 5 and 6 membered ring ketone. Planck's rule. This rule was formulated by Planck on the basis of experimental observation of the ease of formation of cyclic anhydrides and ketones by distillation of dicarboxylic acid according to relative positions of two carboxylic groups. According to the rule, distillation of 1,4 and 1,5 dicarboxylic acids give rise to cyclic anhydrides, whereas 1,6 and 1,7 dicarboxylic acid yields ketone. 1,8 and higher dicarboxylic acid remains unaffected. Planck's rule can be used for determining the size of the ring as well as the chain length of the dicarboxylic acid. For this purpose, a double bond is introduced by suitable method in the given compound, whose ring size is to be determined. The saturated compound thus obtained is subjected to oxidative cleavage with KMnO4 to get a dicarboxylic acid. The acid is heated with acetic anhydride and distilled. If a cyclic anhydride is obtained as the product, the acid is either 1,4 or 1,5 in nature. If a cyclic ketone is formed, the acid is 1,6 or 1,7. If there is no change, the acid is 1,8 or higher. The structure of the acid in turn reveals the size of the ring. Thorpe-Ziegler reaction. On heating in the presence of lithium diethylamide, an alpha-omega dinitrile, that is a dinitrile in which nitrile group are attached to terminal carbon atom, undergoes intramolecular condensation to form cyclic aminonitrile. This is changed into cycloalkane as illustrated below. The first step in the reaction involving cyclization takes place only at a very high dilution. It is referred to as Ziegler high dilution technique. Thorpe-Ziegler reaction is particularly suitable for the reaction of higher ring compound. Damjanov rearrangement. This reaction provides a method of expanding and contracting alicyclic ring system through the formation of carbocations. The carbocations themselves are obtained by the deamination of alicyclic amines by treatment with nitrous acid. Once formed, the carbocation undergoes its characteristic reactions, that is addition of nucleophiles, elimination of a proton, rearrangement to a more stable carbocation. As a result, different products are formed including ring expansion or ring contraction products. Ring expansion. When cyclobutylmethylamine 1 is treated with nitrous acid, we get four products: cyclobutyl carbinol, meth- methylene cyclobutane 2, and formed without involving any ring expansion. At the same time, cyclopentanol 4 and cyclopentane 5 are formed by ring expansion. Ring contraction: when cyclobutylamine 6 is treated with nitrous acid, cyclobutanol 7 is formed without any ring contraction. At the same time, cyclopropylcarbinol 8 is formed by ring contraction. It may be noted that when carbocation initially formed carries the positive charge on the alicyclic carbon, it leads to ring contraction. On the other hand, when the initially formed carbocation carries the positive charge on the carbon alpha to the alicyclic ring, ring expansion takes place. Hydrogenation of aromatic compound. Cyclohexane and its derivative can also be prepared by the hydrogenation of benzene and its derivatives. Condensation of suitable dihalides with malonic ester or acetoacetic ester followed by hydrolysis and decarboxylation. In the presence of sodium ethoxide, active methylene compounds such as malonic ester and acetoacetic ester condenses with suitable dihalides to form cyclic diesters. These are these on hydrolysis and decarboxylation yield cycloalkanes. Cyclopropane monocarboxylic acid is then converted into cyclopropane through a sequence of reactions. It may be noted that this acid cannot be directly decarboxylated by heating as it leads to cleavage of the ring. Acetoacetic ester may also be used in place of malonic ester in this reaction. The ketone obtained above is suitably treated to get the corresponding hydrocarbon. Physical properties. In their physical properties, cycloalkanes resemble the corresponding open-chain compounds, although they have somewhat higher boiling points and densities. For instance, the first two members of cycloalkane are gases, while higher members are liquid. They are non-polar in nature and, as such, insoluble in water but soluble in organic solvent. Some of them, such as cyclohexane, are good solvents themselves. Chemical properties. The general chemical behavior of cycloalkanes is similar to that of corresponding open-chain hydrocarbons. Like alkanes, cycloalkanes also contain only carbon-carbon and carbon-hydrogen sigma bond and are therefore quite inert toward chemical reagent and undergo only a few substitution reactions. It must be emphasized, however, that cyclopropane and cyclobutane differ considerably from their higher homologues. This is because the cyclopropane or cyclobutane rings are not very stable and have a tendency to open up and form addition products. As such, they resemble alkenes in undergoing some addition reactions, but they are less reactive than corresponding alkenes. Few reactions of cycloalkanes are described below. Reaction with halogen. Generally speaking, cycloalkanes undergo free radical substitution with halogens at higher temperature or in the presence of light. In case of cyclopropane, however, bromine and chlorine break the ring system in the presence of FeBr3 or FeCl3 and higher temperature and high yield open chain addition products. Reaction with halogen acids. In general, cycloalkanes do not react with halogen acids. However, cyclopropane adds on halogen acids to form open chain alkyl halides. Addition of water. When heated with concentrated H2SO4, cyclopropane but not other cycloalkanes adds on water to form alcohol. Reaction with hydrogen. When heated with hydrogen in the presence of nickel, cyclopropane and cyclobutane form open chain addition products while higher cycloalkanes do not react. Reaction of cyclobutane takes place at a much higher temperature than required in case of cyclopropane. It may be noted that of the cycloalkanes, cyclopropane is most reactive since it undergoes many addition reactions accompanied by ring cleavage. Next comes cyclobutane, which undergoes addition of hydrogen while the rest of cycloalkanes do not form addition products. Relative stability of cycloalkanes. Beer strain theory. During the earlier stages of their study, cycloalkanes containing up to only 6 carbon atom ring could be prepared in the laboratory, and the rings containing 7 or more carbon atoms were unknown. It was also observed quite early that like open-chain alkanes, cyclopentane and cyclohexane are quite stable and do not undergo addition reactions. On the other hand, cyclopropane and cyclobutane were found to be relatively much less stable and capable of undergoing even addition reaction through ring cleavage. The difference in relative stabilities of different cycloalkane was initially explained in terms of Bayer's strain theory. Bayer's strain theory. According to tetrahedral concept of carbon, a carbon atom bonded to four other atoms lie at the center of a tetrahedron, and the angle between any two bonds is 109 degree 28 minutes. Adolf von Baer in 1885 argued that any departure from this position leads to a strain in the molecule, as a result of which the stability of the molecule decreases. On the basis, Baer proposed a theory now known as Bayer's chain theory. The important points of this theory are: first, the carbon atoms constituting the rings lie in the same plane. Consequently, the bond angle between the adjacent carbon atom of the ring no longer remain 109 degree 28 minutes, which is normal bond angle for tetrahedral carbon. On the other hand, different rings have different values of this angle. For instance, the cyclopropane carbon ring is triangle having carbon-carbon-carbon angle of only 60 degree. Second, any deviation, positive or negative, from the normal tetrahedral bond angle of 109 degree 28 minutes during the formation of a ring produces an internal strain in the resultant molecule, which makes the molecule unstable. Positive deviation means that the angle is compressed, while the negative deviation means the
angle gets expanded. Third, the greater the deviation from the normal angle, the greater is the strain and therefore the lesser is the stability. It may be noted, however, the sign of deviation makes no difference. Fourth, the more stability of a ring system, the more easily it is formed. Thank you.